Good afternoon. During the first part of the lecture of today, I will introduce the notion of osculating plane and osculating circle. So let's consider a unit speed curve in Rn. And let's fix a point in I such that the curvature of the curve at t0 is non-zero. Now let's consider the second order Taylor polynomial of gamma at time t0. This is given by the following formula: gamma t0 plus h is approximately equal gamma t0 plus h gamma prime t0 plus h square over 2 gamma second t0. The reason why we write approximately equal is that when we write down a second order Taylor series for a function, there is an error that here we are omitting, denoted by EH, and in this case, that is the case of a second order Taylor polynomial, satisfies the following property: the limit as h tends to 0 of the length of EH over h squared, this is equal to 0. Now let's think a moment and let's try to write down these two vectors in terms of the unit tangent vector t at t0 and the unit normal vector at t0. So by definition, the tangent vector, the unit tangent vector at t0 is given by the velocity vector at t0 divided by its length, but by hypothesis this is equal to 1, and vt0 by definition is just gamma prime t0. So gamma prime t0 is equal to the unit tangent vector at t0. What about the second term? Last time we proved that t prime t is equal to the curvature times the length of the velocity vector times the unit normal vector n of t if the curvature at time t is non-zero. The reason why you need this hypothesis is that otherwise this vector is not defined. Okay, so what about the relation, the connection between gamma second and these two vectors here? First of all, we observe that we are considering the instant, the time t0, so I have to evaluate this expression at t0. And then I use the fact that the curve is a unit speed, so this is equal to 1. And now I use again this formula, and I try to compute t prime t0. So t prime t will be equal to v prime t, that is gamma second t, that we can evaluate at time t0 in order to get that gamma second t0, which appears here, is exactly t prime t0. And by this formula we get that gamma second t0 is k t0 times n t0. So let's erase the right hand part of the blackboard and write that this polynomial here is also equal to gamma t0 plus h t t0 plus k square k t0 h square over 2 times n t0. This formula says the following. It says that the displacement vector dh, defined as a gamma t0 plus h minus gamma t0, is equal to h t at t0 plus k t0 h squared over 2 times n t0. So this means that it has non-zero components in the direction of t and n. And if we introduce some new notation, precisely I will denote by xh the component in the direction of t. This is given by the inner product of dh with tt0. By this formula we get that is approximately equal to h, is this factor here, and the component yh in the direction of nt0 is approximately equal to this factor here. So it is equal to k at t0 h squared over 2. We already know that the vectors t0 and then t0 have unit length and they are orthogonal, so they are orthonormal. So this implies that if B denotes any unit orthogonal vector, any unit vector orthogonal to t0 and t0, we can say that the component of the displacement vector in the direction of B satisfies this formula. dH multiplied by B is approximately equal to 0. Now let's try to make a picture. Suppose that this is the curve gamma, the trace of the curve gamma. Suppose that this is gamma t0. Suppose that this is t at t0 and this to be n t0. Then what is the information contained in this formula? In order to explain this, I have to sketch also another vector. Suppose that this is gamma t0 plus h, then this vector here is the displacement vector d of h. And now let's give a look at the plane spanned by these two vectors. This is what we call osculating plane at time t0. And let's ask ourselves what is the relation, the connection between x of h and y of h. Clearly, these two functions satisfy this formula: y of h equal kt0 over 2 times x h square. So this is the equation of a parabola. Having its vertex at the point gamma t0. So let's try to sketch this parabola. For example, let's suppose, and this parabola approximates gamma in a neighborhood of gamma t0. Why in a neighborhood? Because the smaller h is, the better is approximation. What I want to tell you now is that there exists another curve which approximates the curve, the trace of gamma in a neighborhood of gamma t0, and it is a circle. This circle is called osculating circle. So osculating circle. This is a circle in the osculating plane. Centered at the origin. That means the point gamma t0. Why? Because the origin of the osculating plane is the tail of these two vectors. And the radius one over k at t0. This circle could be parameterized by the following formula. So parameterization C of S equal to 1 over k t0 times cosinus of S times t0 plus sinus of S times n t0, where S varies in 0 2 pi. Now, if we sketch a circle having radius 1 over kt0 and center the point gamma t0, it's not clear how this circle can approximate our curve. So even though this is the definition, the position of this circle is not for the moment optimal. We will prove that the translated version of the circle described before precisely having center at epsilon t0 equal to gamma t0 plus 1 over k t0 times n t0. Approximates gamma in a neighborhood of gamma t0. So essentially what I'm going to do now is to present to you the solution of exercise 1.42. Okay, so essentially now I will recall the hypothesis we are using. So we have a unit speed curve gamma, unit speed curve gamma such that its curvature at t0 is non-zero. Then for h positive small, the three points gamma t0 minus h, gamma t0, gamma t0 plus h, they are not collinear. Why they are not collinear? Very easy. Let's look at the formula we wrote down on the blackboard before. Gamma T0 plus H. This is approximately equal to gamma T0 plus HT at T0 plus K T0H square over 2 and T0. And if we write down the Taylor polynomial, when plus h is replaced by minus h, we get gamma T0 minus h T0 plus KT0 h square over 2 times n at T0. So why these two vectors and gamma T0 are not collinear? Very simple. It's because of the presence of this term, this one and this one. If this term would not be here, then gamma T0 plus h, gamma T0 minus h, and gamma T0, they would belong to a straight line which passes through gamma T0, and it is parallel to the vector t at T0. So they would lie on this straight line. Because of these two terms, it's not the case. So we have that gamma T0 plus h is located here, and gamma T0 minus h is located, for example, here. If these 3 points are not collinear, then there exists a unique plane pH containing them, and it is also true that there exists a unique cycle denoted by CH containing them. What is possible to prove is the following. 1. As h tends to 0, pH tends to the osculating plane, and second, as h tends to 0, CH converges to the osculating circle, translated at epsilon t0. Epsilon t0 is the vector I described before, and it is gamma t0 plus one over k t0 times n t0. Okay, how to prove one? One is essentially immediate because we have to use this Taylor polynomial, and just let h tend to 0. So what happens? It happens that gamma t0 plus h and gamma t0 minus h, they are given by, for h small, gamma t0 plus a vector which is a linear combination of t0 and n t0 in both cases, but since by definition t0 and n t0 span the osculating plane, then pH tends to the osculating plane. What about the second statement? This is a bit more difficult, but let's try anyway. So let's erase this part. Let's define f of s to be the function given by this formula, gamma t0 plus s minus pH, distance length squared, where pH is the center of CH. CH is the unique circle containing gamma t0 plus h, gamma t0 minus h. Let's observe that this function satisfies the following chain of identities: f of minus h is equal to f0, and this is equal also to f of h. Why? Because if I replace s by minus h, this is the distance between the point gamma t0 minus h and the center of the circle, If I replace S by 0, I get gamma T0 minus pH whose length is square, so this is the square of the distance between gamma T0 and the center of the circle. And if I replace S by H, I get the square of the distance between gamma T0 plus H and the center of the circle. But by construction, the circle passes through the points gamma T0 plus H, gamma T0 minus H. So this function takes the same value at these three values of the variable S. Then we can use the mean value theorem. We will do this 2 times. The first time for the interval minus H 0. The second time we will work on the interval 0 H. And in the first, as a result of the first application, we get that there exists delta 1 such that, okay, let's be precise, in 0H, such that f prime of delta 1 is 0. Precisely, the mean value theorem says that f prime delta 1 should be equal to the difference of the function f at the boundary point of the interval. So they are minus h and 0. And we have to divide by their distance. But in this case, we get 0 because f at minus h and f at 0 is 0. The second application of the mean value theorem tells us that there exists delta 2 in minus, sorry, I made a typo. This is minus h is 0. So there exists delta 2 in 0h such that f prime of delta 2 equal to 0 or for the same reason. And then we apply the mean value theorem a third time. We work on the interval delta 1, delta 2. And we have the existence of a point that I will call epsilon in delta 1, delta 2, such that the second derivative of epsilon is 0. Please note that when I apply the mean value theorem for the third time, the function I am using is the derivative of f. But we get once again 0 because of the definition of delta 1 and delta 2. Okay, so let's erase the picture and let's compute the first derivative of f and let's see what does it give us this formula. So f prime of s, it is easy to compute, is here. This can be computed as the derivative with respect to s of the inner product of gamma T0 plus s minus pH with itself. sorry, why? Because this inner product is exactly the square of this distance. Okay, so it is easy to get 2 inner product of gamma prime T0 plus S, gamma T0 plus S minus P of H. And then if we replace delta 1 or delta 2, we get F prime of delta I. This is equal to 2 gamma prime T0 plus delta I, gamma T0 plus delta I minus pH and this is 0 according to what we found before. Then we have to continue because we need the second derivative of f. So f second of s is the derivative of this function here. So we will get 2 terms. The first one is the inner product, twice the inner product of the second derivative of gamma times this vector, and the second term is the product of gamma prime T0 plus S and the derivative of this term here. But the derivative of this term here is exactly gamma prime T0 plus S, so we can write 2 inner product of gamma prime T0 plus S times itself as the square of the length of this vector. So let's recapitulate. The final result is 2 gamma second T0 plus S, gamma T0 plus S minus pH plus 2 times the square of the length of gamma prime T0 plus S square. So we need to compute f second of epsilon. So f second of epsilon is 2 gamma second T0 plus epsilon gamma T0 plus epsilon minus pH and then there is one more term plus 2 gamma prime T0 plus epsilon whose length is squared. Okay, now we know that this is 0 because we found it before. Now I can erase this part of the blackboard. Now we take the limit as h tends to 0. If we do this, delta 1 will tend to 0, delta 2 will tend to 0, and epsilon will tend to 0. Why? Because delta 1 belongs to this interval, delta 2 belongs to this other interval, and epsilon belongs to delta 1, delta 2. So let's erase this part. So if delta 1, delta 2, and epsilon tend to 0, we get 2 gamma prime T0, comma gamma T0, minus P0 to be equal to 0. And we get also 2. So these come from here. And from here, we get 2 gamma second T0, gamma T0, minus P0, plus 2 gamma prime P0. This is also equal to 0. I have to erase this arrow. Okay, so what we got here? The first formula says that gamma T0 minus P0 has a component in the direction of gamma prime T0, which is nothing but then T0 equal to 0. What about the second one? So first of all, what is this? This is the length. I think here there should be a square. Okay, anyway, the result does not change. This is the length of T0, which by definition is 1. So if I rewrite this identity after dividing by 2, I get gamma second T0, gamma T0 minus P0 is equal to minus 1. Okay, so remember that P0 is the center of the circle C0. In order to understand the meaning of this identity, we have to understand what is gamma second T0. But this is very easy. Why? Because since the curve is a unit speed, and as I wrote before, we have t prime t equal kt times nt, then I omitted the term length of v because this is 1. Then since t of t is gamma prime t, we have t prime t, sorry, we have t prime t equal kt n of t from this formula, but also gamma second t. So we can evaluate at t0. We get gamma second t0 equal k t0 and t0. So this formula gives us the following. It gives us k t0 and t0, gamma t0 minus p0. This is equal to -1. That is nt0 comma gamma t0 minus p0. This is -1 over k t0. Now we have almost finished it. Because this means that gamma t0 minus p0 has a component in the direction of nt0 equal to -1 over k t0. We have finished it because using this information we can write down the following. We can write down that gamma t0 minus p0, this is -1 over k t0 times nt0 plus 0 times tt0. So these has no importance, and we get that p0, this is equal to gamma t0 plus 1 over k t0 times n t0. This was exactly epsilon t0, the vector I introduced before. This is the end of the exercise because we proved that the center of the circle which passes through gamma t0 plus h, gamma t0 and gamma t0 minus h, if h tends to 0, tends to the translated center of the osculating circle. Okay, the next topic of today is the study of plane curves. In order to study plane curves, we introduce a linear isomorphism denoted by R90, defined in R2 with values in R2 as follows: R90 of x, y is a vector given by minus y, x. Please observe that if I compose R90 with itself, I get minus the identity. Precisely, according to this definition, I get that R90 of xy is a minus yx, and then R90 of minus yx is equal to minus x minus y. For which reason? This is because R90 exchanges the component of a vector and changes the sign of the first component. So minus yx becomes x minus y, and then if we change the sign of the first component, we get minus x minus y. So the conclusion is that R90 composed with R90 is minus the identity. Now let's suppose that gamma is a plane curve, that is, it takes value in R2, and it is a unit speed curve. We have seen in the past that for a unit speed curve, a t, the acceleration vector, is orthogonal to the velocity vector. This is because of this hypothesis. Now let's consider the vector R90 of V. It is clear by the definition of R90 that also this vector is orthogonal to V of t. Why? If V of t is V1t, V2t, then R90 V of t is equal to minus V2t V1t, and it is clear that the inner product of Vt with R90 of Vt is 0. So the conclusion of this observation is that At and R90 V of t are orthogonal to V of t. This means that they are parallel to each other. They are parallel to each other. So we can write A of t equal to a scalar function kst times R90 V of t. Ks of t is a function defined on I, of course, with values in R, known as sine curvature function, or simply sine curvature. Let's make a picture. So suppose that this is the curve gamma. Let's fix a point on this curve, and suppose that this is V of t1, so this is gamma t1. Then for this curve, the acceleration point this way, so this is A of t2. Instead, if this is gamma, this is VT2, this is a, sorry, I have to use a blue color, AT2. Then of course there are also the vectors R90 VT1, R90 VT2 to sketch. And in this case, the vector R90 VT1 sorry, this is a 1 points this way, and in this case the vector R90 VT2 points this way. We will see the reason why this is true later. So in this case we have that KST1 is positive. Why? Because these two vectors point in the same direction. Instead, in this other configuration we have that KST2 is negative. Why? Because these two vectors point in the opposite direction. Okay, so the first lemma I want to show shows the connection existing between the sign curvature and the curvature. So lemma 1.37, we have that the absolute value of KST coincide with the curvature KT. Let's prove it, it's very easy. By hypothesis, the length of V is equal to 1, and this will be equal also to the length of R90 V of t because of its definition. I would like to make one more remark about R90. I had to do this before. The reason why the notation we use is this one is that this rotation, this isomorphism corresponds to a rotation of by 90 degrees in the plane. So it is now clearer that if you have a vector of length 1, also its rotation by 90 degrees has a length equal to 1. Okay, so by proposition 1.31, since the curve has a unit speed, then the curvature kt is given by the length of AT. Now, by definition of R of Ks, which is this, AT equal to KST R90 of Vt. These two vectors have the same length. So this is equal to the length of KST times R90 V of t. But this vector here has a length equal to 1, is written here. So this is equal only to the absolute value of KST. We proved KT equal to the length of, the absolute value of KST. Okay, one more remark. The equation star given by this equation here can be also written as KST equal to the inner product of AT and R90 V of T. So in other terms, KST is a component of AT in the direction given by R90 VT. I would like to give the definition of KST for a curve which is not of length of speed 1. So if gamma is a regular curve, then for all t in I have the following formula. We have KST given by the inner product of AT with R90 VT over length of V of T divided by the length of VT square, and this is also equal to AT, R90 V of T divided by the length of V T cube. Okay, that's all for today. Thank you for your attention.